was the derivation of the I is coming from the strain pattern that you have, okay, over the beam, right? You have large strain at the extreme fiber at the top and at the bottom, all right? And then smaller strain up to down to 0 at the neutral axis. So you integrate the strain, okay, multiply by the E, you get stress, and then you integrate through the cross section, okay, you get the moment, all right, and then moment was given as the E. Well, it is somewhere there because the E has to multiply by the strain, okay, so the E multiplied by strain, the I comes up with the cross section, okay, and then the curvature describe the strain distribution. Okay, so these relationships hold. So M equals to EI phi. You can find out more how we come up with this. Okay, it is sort of undergrad things, but should we? Huh?
Strength of materials.
Yes, strength of material, mechanics of materials, undergrad things. If you want to elaborate a little bit, okay, if this is the neutral axis, all right, your curvature, this is your curvature, okay? So curvature is at the point, at one point x, okay? You know that at that point, there's a change of the angle, okay? So this curvature, if you have this curvature multiplied by this height, if we call it C, okay? So C could be anywhere, all right? So at one point, your C, okay? At this point, you will have the phi multiplied by C. This gonna describe your strain, okay? And then you have your strain, you multiply your strain by elastic modulus. So take the elastic modulus multiplied by E multiplied by your strain. You get stress, okay? You get stress, you want force, okay? Force will become the B multiplied by DC. DC is the infinitesimal thickness. If you set this axis being the C, so the C is the infinitesimal thickness. And then that layer is gonna produce one force, okay? Assuming that the B is constant if it is the rectangle cross section. If it is not, the B will be the function of C, okay? So that details in strain of materials. Alright, but if we assume that the cross section is just like this, the B and the total height is the H, like this, okay? Now what do we have? We have the strain, we have stress multiplied by this, we have force. Force multiplied by moment arm. If you want to get the moment in this cross section, so moment arm which refer to the neutral axis. Alright, neutral axis is here, the C is measured from neutral axis. Upward C will be positive, downward C will be negative. Alright, so we have C multiplied to the force, you get moment. But this moment is produced by just this force over this infinitely thin layer. So we need to integrate, okay, through the whole cross section. So integrate with respect to C, from C being the minus H over 2 to H over 2. Okay, so we have C and C, we have C squared, you integrate, you get C cubed over 3. You have the E, you have the curvature. Curvature doesn't change with respect to C. Curvature is changing with the X. Okay, in the beam, your curvature is changing along the x-axis. Alright, what else? C is there, B is there, right? Okay. And then you evaluate this from H over 2 to H over 2 minus, okay? If you have H over 2 to H over 2 and the C is cubed, then you find that it's gonna be h cubed over 8 multiplied by 2. Okay, evaluate from here to here, multiply by 3 over here, and b over there, and c over there is equal to m. So we will end up with b times e times b h cubed over 12 equals to m. And the bh cubed over 12, this thing is the I, alright? So second area moment of inertia. So that constitutes these relationships of phi e I, okay, equals to m. So if you end up with the bending moment diagram, you can plot curvature diagram or the m over ei diagram. Okay. Now your ei, it depends. Ei could be varying. Okay, but generally what you learn in the undergraduate level, your EI was constant. Okay, the life is hectic enough, so your professor is kind enough to just keep the EI constant. I'm not that kind professor, so I will not keep your EI constant. Anyway, you will learn more, okay, how to play with this, but well, I am unchaining you, right? You have some change in your body, okay, so you are still framed within this constraint, okay? We try to unchain you, so you learn things and then you have flexibility to do things that you may not be able to do in the past. Okay, so the M over EI diagram, if the EI is constant, for example, in this case, if I have this BMD, and if the EI is constant throughout, you're gonna find the, so this is BMD, so this is the M over EI diagram or the curvature diagram. So the shape will be alike. This is just scaled by the EI. However, if you are talking about the beam that has, maybe this is 1 EI and this is 2 EI. So one part of the beam is more rigid than another part. Then the M over EI diagram, well, you have the same BMD, okay? With the same BMD, but different M over EI diagram, you're gonna have this thing. Whoop, whoop. So your M over the EI diagram will be not just like the original BMD, okay? Because your EI is changing. Well, actually, you have seen something like this in a strength of material already, I think. But okay, just you will just see it, and you will see something that is even more interesting, like the cross section will not be just EI and 2 EI. It will be EI over here and 2 EI, and then varying in between. So your beam could be varying in depth, okay, and that causes your EI to be a function of X, okay. So you still can play with this sort of situation. All right, this is just the what? Just a picture that, okay, what you may confront with. Actually, in reality, you may end up with it. Sort of this thing like the bridge, okay? Balanced cantilever bridge, okay? Large cross section at the pier and then reduce cross section to the mid span and then larger again close to another support. Okay, so this always occur in your life when you practice, but you just cannot do it for now. But it is not just the case that it's just a crazy case that professor in university bring it up to make it difficult in the exam. No, okay? This is your real life, right? So you find this one day if you design a bridge. Okay.